postdoctoral scholar at the California Institute of Technology. While at Scripps, he developed a theory to represent the short-term deformation process accompanying earthquakes, glacier retreat, lake drainage, and monsoons. Today, he invites you to relax with him as he shows you how the software he has developed can be used in education and research. So, Sylvain, it's all yours.
Thank you so much, Lorraine, for this introduction. So this seminar is an introduction to Relax, which is a software part of the CIG community. And it is a semi-analytic Fourier domain solver, and equivalent body forces for quasi-static relaxation of stress perturbation. Let me use the slide here. So Relax can be used for a variety of static and quasi-static calculations, including earthquakes and surface loads. It can be used to compute Coulomb stress between quasi-static and static Coulomb stress transfer, postseismic transients, and study the effect of variations of surface loads on deformation of the lithosphere. So today I'm going to talk about Relax, and I'm going to give a practical introduction to how it works. So I'm going to assume that you have installed the software, maybe played with it a little bit, and had a look at the documentation. But I will still cover things in detail and will answer any practical question, even simple. So we will look at 3 examples of what Relax can do. One will be the quasi-static stress transfer between faults. So this is a typical Coulomb stress calculation, but not only we're going to compute the static stress transfer between an earthquake source and a fault receiver, but also the time-dependent stress transfer due to quasi-static processes. Then we're going to look at an example of afterslip following an earthquake in a thrust environment. We're going to look at how to set up the variables and the input parameters to make this calculation. And then we're going to look at how we can make viscoelastic deformation models that incorporate geological structural data to make models that are geometrically realistic. And then, if time allows, we're going to discuss some real research examples that used Relax. So we're going to use the example of Chichi earthquake and the El Mayor earthquake. So, okay, going down. So the official webpage of Relax, which is in version 1.0.4, is on the geodynamics.org website. And there you can find source code, the binaries for Windows, for Linux, for Mac and CentOS platforms, and the documentation. These binaries are always dated, and there is always a newer version of the code, a developer version, and the code is maintained and controlled with version control software, which is called Mercurial. And so to access the entire history of modifications of the code, you can go in a terminal and type the command hgclone, the address of the repository and the local directory, and you'll get all the source code and examples and everything. To install the code, you can also use Think for Mac users. So if you have a Mac, you can go into a terminal window and type Think install Relax, and you will have the binaries and the manual page and all the dependencies in terms of libraries. So Relax does only a calculation. What is interesting to do is to look at the results in 3D or in map view. And so far, Relax is interfaced with Paraview, which is a free software to look at deformation or other objects in 3 dimensions. And it is also well interfaced with GMT, which is another free software, which is a powerful tool to visualize and create maps of displacements and incorporate other geophysical information. Once you've downloaded the software and you have passed some sort of sanity check, you can try to learn about how to set up your own input files. To do that, I encourage you to look at the documentation. It's also available on the Geodynamics website, and it describes how to run examples and how to visualize the data with GMT and Paraview. So another more detailed version of the documentation is available in the manual page, which is only accessible with Unix. So to see that, you go again on a terminal, if you have Unix or Cygwin for Windows users, and you type man relax, and it gives you access to a long document that describes in detail all the input file parameters. So an example of the header of the manual page is on this slide. Okay, so before we go into these examples of these very specific examples, I'm going to describe the basics of how we set up the simplest input files. That is the mesh, the constitutive parameters, and some faults. So to do that, to set up a model, to have a model running, you need to set up the computational space. That is the mesh where the calculations are computed. So to do that, you need to provide two things: how many samples you have in one direction. So I call that SX1, SX2, and SX3. This is the grid size in terms of memory. So the larger these numbers, the more memory Relax will be using. But the actual physical space of the model is these numbers multiplied by sampling size. And that I call dx1, dx2, and dx3. So the product of sx1 times dx1 gives you the spatial dimension in one direction. So in the horizontal direction, the distance covered by the grid is sx1 times dx1. In the depth direction, it's only sx3 over 2 times dx3. That gives you the physical extent. So once you have that, you have a mesh that represents some sort of flat Earth approximation. And then you need to set up the constitutive parameters. Relax assumes homogeneous elasticity. So you have to describe the Lamé parameters, lambda and mu, lambda and the rigidity. So in this example, I've put 30,000 megapascal, so 30 gigapascal for the Lamé parameters. And then you can also use a gravity constant, and this gravity constant is a wavelength that is representative of efficient gravitational rebound, so restoring force due to buoyancy. So this is homogeneous to 1 over distance. This is a wavelength. And 8.33 10 to the minus 4 is a good number for the Earth. So don't change it. And after you've done with this, you have a mesh, you have constitutive properties. You can just define a list of fault segments or fault patches where you impose a relative displacement. So somewhere down in the input file, you have to prescribe for each fault the slip that occurs in this fault, the position where the fault begins, its length and width, the strike angle, the deep angle, and the rake angle of the slip. So these numbers used a strict convention for which by default the strike-slip displacement is left lateral. The default deep slip displacement is a thrust, and then varying the strike angle, the dip angle, and the rake, you can have oblique motion and faults of arbitrary position and orientation. When you want to describe structurally rich geometry, you have to discretize the fault into piecewise planar components. This is usually a good assumption, a good strategy, and so therefore for complicated geometries you can have a series of hundreds of little fault segments. One important thing when you set up your input file is to always remember that x1, x2, and x3 form a right-handed reference system, and x1 is pointing north. So x1 is north, x2 is east, and that's a mistake something people forget when they set up their input file. So to set up the simplest input file for Relax, you just have to specify the grid, the constitutive parameter, and the source. And then you have to set to 0 a number of other things that are not used. But this slide shows the smallest input file that you can ever do in Relax. So let's just, that's the complete input file. This is assuming that this is embedded in a script file. So the first line is Relax with some options. And then it says lower than EOF for end of file. And everything from that until the EOF statement at the bottom is considered an input. You can hard code these numbers in the input file, or if you are using a Unix terminal or Cygwin for Windows, you can actually use scripting in there and use some variables and other things. Everything that you can do with scripts otherwise. So in this example, there's just only one fault segment, and the slip is positive, it's 1, and the dip is 90, so this corresponds to a vertical left lateral strike slip fault. Okay, so now if you want to extend this to a complex fault geometry, then you have to, the only thing you have to do is to add fault segments. And this is an example of what you would see if you loaded the Coseismic slip distribution of the Landers earthquake. This is the numbers that you get using the slip distribution model of Fialco. And this model has, for example, 426 individual fault patches. So in the input file, you can copy and paste all these numbers directly in the input file, or you can save them in some sort of a database file. So this, which is the case in the example provided. So if you go in the Relax directory and then examples, Mojave, faults, you will find a file called landers_kilometers.flt, and this has the list of all these fault segments. So in the Landers input file that you can find in examples, Mojave directory, you can either copy and paste all these numbers, or you can use a Unix command. So an example of that is cat faults landers_kilometer.flt, all of it in back quotes. Or you can do some more advanced scripting. So you can filter some of these faults segments, or you can change their amplitude, the amplitude of slip, for example, change the unit from meter to centimeter if that's something you prefer. So to do that, a simple thing is to use awk, which is a standard Unix command. So, and that's the example that is provided at the bottom of the slide. So if we look at the second red line, you see that we load the fault's landers kilometer.flt and we oak that, and we only print the lines for which the fifth column is greater than 2 and lower than 20. So the fifth line is not, so the columns are index, slip, x1, x2, x3. So the fifth line is the depth of the fault. And so that command only uses the fault patches that are below 2 kilometers. And the line above is exactly the same, but instead of printing the line, it counts the number of elements that are below 2 kilometers. So that's a simple example, and you can do other things. You can join different files and use all the power of Unix scripting. All right, so now you can run this example. This is in an input file called landers.sh. That creates a new directory called landers. And in this directory, you'll find a series of files that corresponds to GMT outputs and Paraview outputs, among others. So to visualize this calculation, you can use GMT. So in the Relax distribution, you'll find a lot of utility scripts for post-processing and visualization. One of them is called grdmap.sh. So you can type in a terminal grdmap.sh-h to have a list of the possible options. And what it does is generate a postscript file that shows the map view of displacements. And this postscript file is always terminated with a little cookie that says how the script was generated using this command. So if you type in a terminal tail-n2 landers 000-plot.ps, it will show you what grdmap command you used to generate it. So you come back a year later to your research project, you want to know how you generated this plot, you can just go there and it's all recorded for you. And the command that I use to generate the plot on the right is this one-line command. So this is grdmap.sh, and then you set the bounds of the map. So it goes from -75 to 50 in both east and north.
Sylvain, I'm going to interrupt you here. I just noticed there were a few questions. If you redirect yourself to the chat window,
So
I think they're on your previous slides.
Yeah.
So.
All right. Sorry, I was in full screen, so I didn't see anything else that was going on. So I have two questions here. All right. So Bill is asking what is the reference point of the slip patches. So I'm going to go up to the convention of the fault geometry, and you see on this slide that the reference position of the fault is the lower left corner of the fault segment. So you'll find many other conventions. Some people like the center of the surface segment. Some people like the true center of the rectangle. Again, this is a convention, so I use the upper left corner. Yeah. So, and then Ahmet has an oak question. Okay, what is C equals 0 in the oak line there? Okay, so this is, so I'm going back to how to read a database file of fault segments and filter them and manipulate them. And basically, I'm using a capacity of oak to do things on the file and then output something only when it's done. So to do that, you separate things in begin, header section, and then what's after is done for every line, and the end section is done after it's done with the file. So basically, before you read the file, you initiate this variable, you set it to 0. Then for each line, you increment this C counter only when you find segments that are between 2 and 20 kilometers. And then when you're done, you just print C. So it's a counter. And it counts how many segments are between 2 and 20 kilometers. So, so that's it. No other questions. All right. So where was I? Visualizing. Okay, so all right. So if you, I was describing grdmap.sh, and basically you set the bounds, and then the v parameter sets the size of the little arrows, the vectors, and the p sets the color scale in units of meters, and the -e can run an extra script, and so this script is also provided. It's called erpatch.sh, and the script is automatically looking into the landers folder for geometrical information. It finds the surface trace of your faults and it plots them. So that's why in this plot you see dark lines that correspond to the rupture. This is done by this erpatch.sh script. You can add other script that plots, say, seismicity or other geological information using this -e option, and you can have as many as you want. All right, so that's for grdmap.sh. You can do a lot of things with that, and I'll show some more examples later. Another great way to visualize the data is to look at it in 3D, and that's great to grow intuition about why do you have, say, vertical displacement here? Like what's happening at depth? What is the complete context of the displacement that gives you the surface features? So it's very instructive to look at things in Paraview. So there is a number of simple things that are exported in the landers folder that help you put things in context. So the computational grid is always exported, so you can see in 3D what is the physical extent of your computational domain. So to do that, you can go to Paraview. So you open Paraview, you click on File, Open, and you load cgrid.vtp. C is for computational, it's the computational grid. Then you click Apply, and you have this very large rectangle that pops on your screen. So usually things happen inside that, so you don't want to hide it. So to do that, you change the surface representation to wireframe, and that shows only the edges of this brick. And then another thing that's very useful is to just load the slip distribution. So to do that, you do File, Open, and you load R fault. R is for rectangular, and -1 means the event 1. So you can have many different events in one single simulation. And so that's the Coseismic slip distribution of event 1, which is the first one. So then you click Apply, and you have these fault segments that appear, and they are all gray. So to see where the slip distribution is focused, you change the representation, the color from solid color to slip. And that should give you a three-dimensional representation of your earthquake slip. And then you can load many other things, which I will let you explore, namely the displacement, the stress components, and then you can open your own objects, like say fault models, or in the case of landers, you can load the SCEC database of faults in California to put your deformation into context. When you do your own slip distribution and you're not sure what it looks like, you can write an input file yourself in an editor and then convert it to Paraview using a simple script command that is included in the util directory. This script is called FLT to VTK.sh, and you give it a slip distribution database, and it provides, it writes another file with a Paraview file that you can read. So it converts something.flt into something.vtp. So you can open that in Paraview and check your geometry before you do complicated calculations. All right, so with this introduction, we can move to several examples. So doing stress calculation is pretty popular. This is the first example that I'm going to cover. So we're going to look at quasi-static stress transfer between faults. And I say quasi-static because we're going to look at both static deformation and Coulomb stress, and also the stress evolution due to postseismic processes. All right, so in this example, we're going to compute the evolution of stress on the Bullion and Lavick Lake faults, which ruptured during the 1999 Hector Mine earthquake due to static displacement on the Landers earthquake and the viscoelastic deformation that followed the 1992 Landers earthquake. So to do that, we're going to define receiver faults where we need to compute stresses, stress components, and projection onto the fault surface. And for that, we're going to use the fault geometry of Simons and others from the 2002 paper. And that fault database is in the directory examples, Mojave faults, Hector mine .flt, Hector_kilometer.flt. So this calculation is available with the distribution of relax, and you can find it in examples, Mojave, Coulomb.sh. So you can run that on your computer and look at the output files if this is working for you. So let's go ahead and add the geometry of receiver faults. So basically one option is to go into the slip distribution database file and copy all the numbers and paste them into the relax input file, and that would look as follows. We'll have 263 fault patches and then a list of all of them with their position, their length, their width, their strike, their dip, and the friction coefficient. So notice that you don't have to specify the rake direction. The rake is actually computed internally based on the stress tensor and the direction of the traction vector on the fault. So basically, relax assume the optimal rake direction. But in the output, it will also provide the stress components in the strike direction, in the dip direction, in the normal direction, and so forth. So you can reconstruct whenever you need. So, but instead of doing this copy and paste procedure, we can also use simple scripts. And the Hector Mine database file has a slip distribution. So it basically has all the information and more. So it provides also a slip distribution, which we don't need, and a rake, which we don't need. But it doesn't provide a friction coefficient. So we just need to add that. So let's look at the second red line in the script. We basically first grep the slip distribution that removes all the lines that are starting with a special character, and that basically removes comments. And then we remove the second column, so we say we send it to Oak, and then we set that the second column is empty, and the 10th column used to be the rake, so we also cancel that. And then we write everything else, and we add the 0.6, which is the friction coefficient. That gives rise to a list of 263 lines. And so, but to count that, we just repeat the same line above, and we pipe that into WC, which is the word counter, and so that outputs the number of lines. So in 2 lines, you're done with that. So then you run the Coulomb.sh example, and that provides a series of a large number of files in the Coulomb directory. And for example, for every patch of the Hector slip distribution, you will find a time series of stress evolution. So in the middle there, you see an example of what is filed in the Coulomb directory. C fault stands for Coulomb faults, dash sigma, so it's a stress, stress information, and 244 is the patch number. And if you look in there, you see 2 comments. One says, well, the position of this patch, the center point in the northeast and down direction are as follows, a bunch of numbers. And then some headers, which are the time. Sigma 11 is the extension in the north direction. Tau S, tau D, tau N, and Coulomb. So tau S is for the shear stress on the fault in the strike direction. Tau D is the shear stress on the fault in the dip direction. Tau is the norm of the traction. So the square root of the square of the 2 previous columns gives you tau. Tau N is the normal direction. It's basically the change of confining pressure. And Coulomb is a linear combination of tau and tau N. So there are many other stress components that are in this file, so you can look at it yourself. I just stripped them out so that it can fit on this slide, but there's all the stress components and so forth. So that gives you a lot of information. And it's a time series because as the viscoelastic deformation goes on, it changes displacement around the receiver fault and it affects the stress. So you can look at how things evolve with time. All right, in Paraview, you can also look at this in 3D. The result is basically the image in the background, which was in fact used for the logo of Relax. So on the left, you have the Landers slip distribution. On the right, you have the hectomine, and it's colored by the intensity of stress change. So to do that in Paraview, you can you go into the Coulomb directory and open R faults d sigma -000, and d sigma is for differential. It is basically the stress change minus the coseismic stress change. So it allows you to look at only the component of stress that changed after the earthquake. So the postseismic contribution. So then you click apply, change solid color to shear stress or other things, and you can look at, you can make a movie of the stress evolution using the play button in Paraview. You also have the cumulative stress component if you wish, and this is instead of R faults dash d sigma, this is in R fault dash sigma. And that includes the coseismic stress change and whatever happens afterwards. All right, so now we move to another example. This is the example of afterslip in a thrust environment. So we're going to use the case of the 2005 magnitude 7.6 Kashmir, Pakistan earthquake and try to simulate the time-dependent afterslip that may occur after this event, based on some assumptions. So the first assumption is we're going to assume that afterslip will occur on a deep extension under fault that ruptured in 2005, and then we're going to assume that the slip accumulation is governed by a rate strengthening friction law, and this is a simplification of rate and tape friction. So to do this calculation, we need a coseismic slip distribution of the 2005 Kashmir earthquake that will basically impose a stress change, and from that we can relax it and predict some afterslip. So to do that, we need to prescribe the afterslip constitutive properties. So the governing law is that the velocity of slip, so S dot, is proportional to the hyperbolic sin of the shear stress divided by the confining pressure, scaled by some friction parameters A minus B, and scaled in time by this gamma dot 0 parameter. So if you prescribe gamma dot 0 and A minus B sigma, then you can actually produce a calculation. And the last thing you need to prescribe is where this slip would occur. So you need to specify an afterslip fault geometry. And that's just the orientation and the dimension of the afterslip fault. So you see the 3D visualization in Paraview to the right. The color scales there represent the coseismic slip distribution, and this is all in the thrust direction, more or less. You can see that it has 2 fault segments. And then the afterslip segments are the ones that are for which you see only the contour. So we only allow afterslip for a deep extension of the first fault, and then another one with a slightly different angle. So you can do that in Relax with just a few lines in the input file. So first, you prescribe the constitutive properties. So you need to specify how A minus B sigma and gamma dot 0 change with depth. And this is done with one line there, and it says, after a depth of 0 kilometer, gamma dot 0 is 10 to the minus 3, so think meter per year, and A minus B sigma is 5 megapascal, and the friction is 0.6. So basically everywhere in the grid, gamma dot 0 is 10 to the minus 3, and A minus B sigma is 5. If you would want these numbers to change, you would have to add a line and indicate the values of A minus B sigma, say, at a different depth, and the value would in fact be interpolated from the surface to this second depth. But that's usually not very well constrained, so it's not used very often. Second element that is critically important is the afterslip fault geometry. And as seen in the snapshot there, there are 2 fault segments. And so you just have to specify again where this fault starts, its length, width, strike, dip, and rake. So these are the numbers that work for this region. And the rake is actually a very important parameter because, as you can see, the one afterslip segment and the coseismic slip distribution, in fact, overlap. And if you used if you would want to relax the stress there without any additional constraints, you would find that, in fact, the best way to do that is to reverse the direction of slip. So you would predict normal motion in this fault. And that's very intuitive, right? The best way to remove this stress is to cancel the slip distribution that occurred. But we don't want that. We want this slip distribution to be basically unchanged, and we want just the slip to increase in size around the coseismic slip distribution. So to do that, you just say that the afterslip has to be in the thrust direction. And in Relax, when you indicate a rate of 90, in fact, you allow 90 plus or minus 90 degrees. Basically anything you want but normal motion. And that's a simple trick that allows you to have overlapping afterslip segments and slip distributions. All right, so this example is available in the Relax release, and you can find it in examples, Pakistan, Kashmir 05, afterslip.sh. So you can go into this file, and there you'll find also instructions about how to run it and how to visualize the data in Paraview or GMT. In fact, every example has information like that, so I encourage you to read it. So you can find for every time step an output file that describes the slip distribution and the stress state on the fault, on the afterslip planes. So an example of that, so you can find it in examples, Pakistan, Kashmir 05, afterslip, and then in the file called 001.s1.crib.dat. So the first 001 stands for time step 1, and so this will change as a function of time. The second, S1, stands for segment 1. So if you want to look at the deeper part of the afterslip, you will have to look at 001-S2, and you will find the same information there. And then that's it. So an example of what this file contains is first positions, x1, x2, and x3. And that's positions of this, I think, the centers of the patches in 3 dimensions. And then you also have y1 and y2. And that's a local reference system that is aligned with the strike in the deep direction. So it allows you to visualize the same data, but on a 2D map. Sometimes it's easier. And then you have a lot of information about cumulative slip, velocity, and components of stress. There is probably 20 or so columns in this file, and I've shown you only a few here for simplicity. So if you're interested in evolution of stress, or evolution of slip, or evolution of velocity, all the information is there. You can also look at the result in Paraview. That's just very well streamlined. So if you have a calculation, just look at Paraview. It takes 2 seconds, and so you know if something's going wrong. So yeah, you'll have a lot of files in Paraview, and the output looks like this one in the snapshot. And you see that shows, in fact, the cumulative slip after, say, a year. And you see that the afterslip is on the down deep extension of the fault, also a little bit at the surface, and you see that it creeped even in the second deeper patch. You can look at the time series of displacement in GMT. So again, you can use this GRD map command. On my computer, I have a link from map.sh to GRD map.sh. So I use these commands interchangeably. And in Unix, you can use this trick with these curly brackets. So instead of plotting one thing, you can plot time step 0, 1, 2, 3, 4, 5, 6, and 7, all with the same color scale and vector scaling and so forth. And that gives you, in a few seconds, a time dependence, an evolution of the surface displacements. So that's also something that you can do really quickly to look at the units, look if the displacement is what you expect, and so forth. Okay, so no more questions from this. I'm going to go into viscoelastic examples. Let's move on for the interest of time. So I'm going to look at how to set up viscoelastic models that incorporate structural data. So beyond the vertically stratified viscoelastic domains. So I used viscoelastic models before. Now I'm going to describe them a little better and then segue into 3D models. So to do that, let's look at a simple viscoelastic model. You can find that in the directory examples, tutorials, run2.sh. And the main difference with the static model is that you have to prescribe a duration of the calculation in time. So you have this line somewhere in the input file that says integration time. That's how long in physical units you integrate the governing equations. And time step and scaling factor. So I often have these numbers set up, 20 years, -1 and 0.5. So when the time step, when you provide a negative time step, in fact, it means, well, don't bother using my time step. Use your own, find the best ones. And I know you're good at this, but I want something even more accurate. So I take your time steps and I scale them by 0.5. So it's twice as accurate. The integration scheme is second order. So when you reduce the time step, you get better results. So -1 is produce the output at every time step. -2 means produce the output every other time step. And that's a way to save memory or disk space. You can also provide your own time steps, and the output will be only written to disk at the times you provided. But in fact, internally, it will do calculation at smaller time steps if needed, just to ensure accuracy. So these numbers are not that important. Basically, you're often guaranteed to have a good computation, even if you change these numbers. So then to set up a viscoelastic domain, a simple one, so a vertically stratified layer, somewhere in the code you have to produce these few lines that are highlighted in red, and you provide the depth at which the viscosity changes. And then everything in between will be interpolated. So if some people are familiar with the Prem model, it's exactly how Prem is constructed. You just tell the numbers where the viscosity changes, and the rest is figured out from there. So in this example, in fact, it doesn't change. So basically, starting at a depth of 2 kilometers, there is a viscosity of, well, this is a nonlinear viscosity. So there's a power exponent of 3 and a prefactor of 5,000. And it goes down to the bottom of the computational domain. And so that's all you need to do. And of course, you need to provide your earthquake slips distributions and so forth. But if you have this information, then the viscoelastic flow will be calculated. All right. And so you can run this example. Run2 runs actually very long, so you can kill it in the middle. That's OK. The output will still be in the files, in the directories, so that's not a problem. And then you can look at the surface displacements using GRDMap command. So if you plot output 2,000, that plots the coseismic deformation, and because that's the 0 time step. If you want to plot only the viscoelastic part of the deformation, or the postseismic part, then you have these indices of time followed by dash relax, and that plots only the postseismic contribution. So that's something you can do. And you have here an example of a velocity field due to viscoelastic flow following strike slip motion and a fault. All right, so now what I want to discuss is how to incorporate structural data about a geological region. So to discuss that, I'm going to use the case of the Kokoxili earthquake in Western China. And this is an earthquake that separates a plateau and a basin, and so you can expect a change in the moho depth and in the elastic thickness. So a simple way to do that and to incorporate without much more information, a simple way to do that is to imagine a step across the fault of the depth of the moho. So basically, the moho depth would look like a Heaviside function in this direction. So one way to do that is to start with one vertically stratified reference model and then to change it using ductile zones. So every time you specify a depth-dependent model, Relax also asks you, well, do you have some zones there where the viscosity is different? So these zones are, you can think of them as like thick faults. And so they are indicated in this diagram there with the orientation of a brick. So that's an elementary 3D ductile zone. And if you specify like the way you would do for a fault, so the strike direction, the width and the length, and the deep angle, you just extrude this 2D object to 3D using a thickness, and that gives you a volume and gives you a brick. And then in this brick, you can say, well, the viscosity changes there. So another thing about Relax is that it's never using, in fact, viscosity numbers. It's using a reciprocal of viscosity. It's called the fluidity. And instead of, we call it gamma dot. And gamma dot is the viscosity, is the rigidity divided by the viscosity. And that's convenient because when it's 0, there's no viscoelasticity, it's elastic. And 0 is a very convenient number in a computer, as opposed to infinity. So, so in this example of the Kokoxili earthquake, you start with a viscoelastic structure that is semi-infinite and starts at 20 kilometer depth with a fluidity of 0.1. So fluidity of 0.1 corresponds to viscosity of 10 to the 19 and relaxation time of 10 years. Then you add a ductile zone that is very large and covers the length of the earthquake and more. And you reduce the fluidity by 0.1. So basically it's now set to 0. So in this region it's elastic again. And you can see in this small snapshot a view of the length of the fault, and it extends down to 15 kilometers or so. And then the contours of this ductile zone. You can see that it's a very thin region of 10 kilometer depth where we want the crust to be thicker. So the way we define that is give it a starting point, then a length of 500 kilometers, a width of 10, so that's in the depth direction, and a thickness of 200. The strike is aligned with the earthquake, so it's minus 81 degrees, and the dip is 90. Because the dip is 90, the thickness here represents some sort of longitudinal extent. And so in the calculation, the fluidity that is used is the sum of the background reference 1D model and the corrections from the ductile zone. So gamma dot 0 plus delta gamma dot 0. And you can use an arbitrary large number of them to construct more sophisticated models. But this example shows you how very simply you can you can design a model that incorporates some realistic features of the geology. Okay, so another example of more complicated example of a 3D viscoelastic structure is the case of a subduction zone. So in the case of a subduction zone, you have presumably cold slab that is that has a viscosity much higher than the surrounding mantle, and this slab is diving down below a continental plate. So basically, you form a situation where you have a mantle wedge and a 3D geometry. And that is in fact very easy to put together in Relax, because if you have access to a patch representation of the fault slab, then you can directly use that and convert it into ductile zones of finite thickness. And so you can extrude down the slab and reduce the viscosity of the surrounding mantle and create a mantle wedge. So the example that I provide here is for the Sunda megathrust in Indonesia. What you see in the Paraview file is, well, the coastline of Sumatra, and you have a contour of the Sunda megathrust, and then the planar surface that is a little lighter than everything else is in fact the depth at which the viscosity, it's basically the asthenosphere depth. It's set at 80 kilometers. And the gray volumes all the ductile zones. So let me walk you through how we do this mantle wedge geometry in 3D. So first, let's look at this red line. You start with a 1D viscoelastic structure where the viscosity is set to 10 to the 18 Pascal seconds, so for the fluidity in units of megapascal years, it's just 1. So it starts at 80 kilometers and it's homogeneous below. And then you indicate the number of ductile zones. I don't know how many, but that's a lot. And then follows a list in orange of their geometry. So assume that you know in some sort of database file the geometry of the Sunda megathrust. You may have obtained this from the USGS slab geometry. So this file indicates the position of patches, their width and their length, and their rake, and their deep angle and their strike. So that's typical of a slip distribution model. Well, from that model, using a simple Unix command, you can convert that into slab geometry that is shown in this snapshot. So to do that, you grab this file, you remove the comments, and then you pipe the result to Oak. And Oak is going to do some simple math on the numbers in different columns. So Relax is expecting an integer, and then the delta gamma dot 0, and then a list of positions and dimensions. So for the integer, Oak can provide that in a variable that's called NR. It's just a counter. It counts the number of lines that it receives. And then I indicate -10. So that's the delta gamma dot. And that's a very large number. So the fluidity will be 1 minus 10 in these regions. So that'd be -9. Viscosity or fluidity cannot be negative. So basically Relax will think, oh, it's 0. That's what you really meant. So put a large number there and you set everything to elastic. And then $2, 3, and 4 are the positions of the patches, and that's the same for the ductile zones. And then 5 is the length in the strike direction, so I keep that the same. And the width, I'm going to set it to 80. And 80 is the depth of the lithosphere everywhere else. I mean, in the oceanic plate. So basically, all the ductile zone will have a depth of 80 kilometers, and they will represent an extension going down of the oceanic plate. The strike I keep, so $6 is there. The deep I keep, and oh no, the thickness I keep, I set it as the width of the patch, and the dip I change it from whatever that is to a rotation of 90 degrees. So I orient the ductile zones down. Basically, it's a simple geometric transformation, and that creates the slab that you see in the snapshot. And then, have a question?
Sylvain, we're actually past the hour now, and we're starting to lose people. I don't know if there's a way we can move through the slides a little bit quicker.
Well, I'm actually done with the examples, so we can just stop there. And everything else I had in case I had more time. So we can just stop there and take some.
Well, I'm going to ask. Okay, well, I'm going to ask the participants. You have the ability to raise your hands whether or not you want to see some of the other examples that Sylvain has and hang in there for a little while longer. We're perfectly happy to keep this webinar open if it's of interest to people. So if you go to the top of your screen, your meeting window, there's this little guy there, and give us an indication of how you want us to proceed. Well, it looks like we have a couple of takers. Let's do this. Let's see if anybody has any questions. So if you have any questions at this stage, go ahead and type them into the chat window, and then when we're done with the questions, and if everybody wants to hang out for a little longer, we will proceed with the rest of what Sylvain has. So we have a few people typing. We just need someone to hit return. So our first question is it possible to couple afterslip and viscoelastic deformation?
All right, so I'm going to answer Anne while Bill is still typing. So that's an example that I cover here for the case of the 1999 CIG earthquake in Taiwan. So this earthquake, well, I'm going to try to be fast. We have some evidence from thermal chronology that there is a very high thermal anomaly below the central range in Taiwan. And as viscoelasticity, viscosity is a thermally activated process, anomalies in thermal structure will lead to 3D structure and viscosity. So this is something that motivates more shallow viscoelastic flow than in other places. And then, of course, based on studies of afterslip and other things, we know that the Coulomb fault, in fact, connects to deeper décollement, and so we can expect some afterslip there. And so this is a situation where you can have strong afterslip, but also strong and shallow viscoelastic flow. So this is a case where it's interesting to connect afterslip calculations and viscoelastic flow. And you basically, in Relax, you basically go ahead and prepare your afterslip like it was alone, and prepare viscous flow like it was alone, and just put them together in the same input file and run it, and you have coupled viscoelastic and afterslip model. So in this example for Taiwan, this is a case where we know that there is a 3D anomaly for viscous flow, but it's poorly resolved in 3D. So the best we could do in this case was a simple boxy structure for viscoelastic flow. And for the afterslip, use the geometry of the deep décollement. And together we could, with this model, together viscoelastic flow and afterslip, we could explain the near field and the far field geodetic data. So yes, that's possible. And that's, in fact, that was kind of the motivation for building Relax. Okay, so now I'm reading the question from Bill. Okay, So Bill is asking about benchmarks, and I do not know if I have a slide ready for that. I think look for it. No, I don't. So in the documentation, you will find benchmarks, and there are benchmarks for strike slip, dip slip, opening dikes, and Mogi sources. And in the documentation, you'll find a benchmark for the Landers earthquakes, and it has 426 slip patches. And the result of this benchmark shows that there are some residuals in the very near field, and that's because the faults in relax are finite, and so you always miss the displacement that is a few samples from the fault, a few samples away from the fault, and but that is by construction, so there's nothing you can do about it. Well, you can make your samples finer and finer, and this goes away, but at some scale, it's always there. And then, second, there are some residuals in the far field, but much smaller, and they are due to fast Fourier transforms that assumed symmetry of the field, of the displacement field. So that is not a desirable property, but we cannot do without it. So it introduces some very slight residuals in the far field. So the solution for that is to make your mesh larger and larger. So that that demands more and more computational resources, but if you have access to that, then that's not a problem. So Bill is typing something. Okay, so Bill is asking whether we can import meshes or if they have to be in relax. So in fact, there is no mesh in relax. This is all implicit, really, and the calculation is done analytically on a Cartesian mesh after a discrete Fourier transform. So that's a strong limitation of relax, that it needs to be a Cartesian mesh, and so far we need to have homogeneous elastic parameters. This is because the solution can be analytic in the Fourier domain if this is the case. There are ways to deal with vertically stratified elastic structure, but using propagator matrices. But so far, this is not implemented in relax. But that's something that would be interesting to do. So no, you cannot import meshes, and you have to stick with the Cartesian mesh. Okay, so Kulali asks about computation time. So well, really depends. It really depends, but it depends basically on the size of your domain. So SX1, SX2, and SX3 control the memory that you need, but also the time that it will take to do a calculation on that mesh. And of course, the number of time steps control the calculation time. So that is greatly varying. But so let's talk about a given time step. So if you use a laptop and 256 cube for a mesh, you can get the results in, say, a time step into maybe 1 second, or maybe half a second. But the computation time scales with n log n. So if you double SX1 and SX2 and SX3, you double n by a factor of 8. And so instead of 1 second, you can expect maybe 12 seconds for one time step. So it is much faster than many other methods for what it can compute. But for a typical research quality research computation with the largest mesh possible and access to supercomputers, I would say one model run will take 2 to 3 hours. So Relax is parallelized, so you can run it on the node of a computer cluster. And then you can use other nodes to run other models if you want to explore the model space. And every model will be computed in 2 hours also. That's typical times. But all the examples I provided, say this one Afterslip, the way it's set up, it's maybe 30 seconds. That's because it's using a smaller mesh. So I must say that if you want to contact me about a specific question you have, and if it's too complicated to talk about it now because you have specifics about fault models and stuff, you can always contact me by email and tell me more about your problem. If you do so, make sure you read the documentation, and so we're on the same, we're in sync with that. And so Bill is asking triangular grids. Huh. Yeah, that's a tough one. So Bill is asking if we can incorporate more smoother geometry that are described with triangular meshes. So I'm assuming he wants to do, say, the Nanyang trough or something else that is well understood geometrically. And the answer is I don't know. I have tried to do triangular meshes. I'm not sure it adds a lot to the resolution of the geometry because Relax is assuming fat faults anyway, so there is always some degree of smoothing that is involved, and so it's not as sharp as you would want it to be. So if it's rectangular or triangular, at some level, it doesn't really matter, unfortunately. This is all because Relax is using an equivalent body force representation of faults, and it's not really a discrete boundary condition inside the model. That makes things much faster and much more easy to set up, but we lose resolution in the near field. So Relax will be more important, more useful to do like gross, large-scale deformation rather than look at a particular fault patch and what it does. So I think that's why I gave up trying to integrate triangular grids. Anne is asking about examples for Mogi source volcano deformation. That's, I think there is one, I'm not sure. There is clearly more examples for earthquakes. That's basically my bias because I study earthquakes. Let me check really quick. I think there is, I'm going to check the repository and see if there is an example of that. Okay, so the answer is no. There is no examples of Mogi source, but there is an input for that. So it's called the number of dilatation sources, and you can describe, all you need to describe is the central point of your magma chamber and the opening in meters. So you don't need strike and dip and all that because it's a point source deformation. But it's described in the manual page. So all you need is substitute faults for Mogi sources. Okay, Kulali is asking about inversion capacities for relax. There's a little bit of that. So there is a script called obsres.py that computes residuals between relax calculations and data. And so if you have different models and you can test them, then the lower number outputted by this script will give you the best fitting model. So that's a little bit of an inversion technique, but it's not a full speed inversion with model space exploration or something. Once relax can run faster than a typical time of 2 hours per model, then we can start thinking about doing Monte Carlo inversions and exploration of model parameters. And that's something I'm very interested in. So I am working right now to implement relax on GPU and other hardware that is much faster. So after that is done, we can start developing more thorough inversion procedures. So I give it a timescale of about 2 years before we see that happening. But I'm very interested in it, and it will be interesting. De rien. All right. Any other question? I'm available for any other question. So. Okay.
So I think at this time we will conclude this webinar. I want to thank everybody for all their good questions and for hanging on this long, and also for Sylvain for his time as well. It's a long time to talk, and he's on, I know, a very busy schedule. So thank you, everybody, and our next webinar will be April the 11th, where we'll have Sarah Minson talking about Bayesian earthquake modeling.
Thank you, everyone, for attending. All right. Thank you, everyone, for attending and for your interest. And don't hesitate to contact me about